Welcome friends to my YouTube channel Sommo Physics. Yesterday I have discussed about the gravitational potential and I took there the example of a thin spherical shell, and we will see that the potential can vary depending upon the location of the point. Okay, that is, we consider three cases: outside, inside and surface. Now, in today, we shall discuss about the gravitational potential due to a solid sphere, and we also did the solid sphere when the point P is outside. Now, today we shall discuss the case when the point is located inside a solid sphere. So, this is a solid sphere. Suppose okay, this is a solid sphere of radius say a, and there is also inner sphere of radius r. Okay, now to suppose the point P is located inside the sphere of radius a, that is at this point, that is the point P lies inside the sphere of radius a, and also located at the surface of the inner sphere of radius r. That means point P lies at the surface of the inner sphere and inside the sphere of radius a. So at first, let us check what will be the potential at P due to the inner sphere of radius r. What will be the potential? Now the potential will be minus G into a mass of the inner sphere. What is that? 4/3 pi r cube rho. Rho is what? Mass per unit volume, right? Divided by r. So this is the potential at P due to the inner sphere of radius r, minus G into m. M means 4/3 pi r cube rho by r. Rho is what? Mass per unit volume. Mass per unit volume. So what will be the result? Minus 4/3 pi r square rho g. That we find easily. Now we have to find out the potential at P due to the rest part, that is this part. So for this reason we consider a spherical shell of radius x and with dx. Okay, to find out the potential due to this part, at first we take a spherical shell of radius x and dx. First we find the potential at P due to this shell, and then we will integrate that expression from x equals to r to x equal to a. So imagine a spherical shell. Imagine a spherical shell of radius x and width dx. So what will be the potential due to this spherical shell? That is, if we consider it dv2, then it will be minus g into what will be its volume. Now the volume will be 4 pi x square dx into rho. Okay, this is the mass per unit volume and this is the volume. 4 pi x square dx is the volume of a spherical shell of radius x and width dx by x. So what will be the result? Minus 4 pi x dx rho into g. Okay, now if we integrate this expression within the limits, x equal to r to x equal to a, that is r to a, we will get the potential due to this rest part. Okay, this rest part, this is the potential due to the thin spherical shell, and if we integrate the expression within x equal to r to a, we will find the potential due to the remaining rest part. Okay, So what will be the result? Minus 4 pi rho g x square by 2, that means a square minus r square by 2. So minus twice pi rho g into a square minus r square. So we get two terms. This is the potential due to the inner sphere of radius r, and this is the potential due to the remaining part of the sphere. And if we add these two terms, we will get the total potential at a point P due to the entire sphere. Okay, so let's do it. Okay, so let's do that. What will be the total potential? What will be the total potential? If we call it V, then V equal to V1 plus V2. So what is V1? Minus 4/3 pi r square rho g minus 2 pi rho g into a square minus r square. Okay, simply this. Okay, simply this. Now if we take minus 2/3 pi rho g common, then what will be the result? We get 2r square plus 3 into a square minus r square. Okay, so what will be the result? Minus 2/3 pi rho g. Okay, we get 3a square minus r square. Since a is greater than r, we write this term as in the first. Now what will be the entire mass of the sphere of radius a? 4/3 pi a cube rho. Now from which we can substitute the value of rho. What will be rho? 3m upon 4 pi a cube. So substitute the value of rho. So what we get? Minus 2/3 pi g rho. Rho means 3m by 4 pi a cube into 3a square minus r square. So pi cancels, 3 cancels, there will be 2. Okay, so the ultimate result will be minus gm by 2a cube into 3a square minus r square. So this is the result. Minus gm by 2a cube into 3a square minus r square. Okay, so here the potential is negative. So this is not a very difficult task. I can recapitulate it. At first you have to find out the potential due to the inner sphere. Okay, so that portion is gone. So remaining, for the remaining other part, you have to consider a spherical shell and find the potential due to that corresponding spherical shell. Then simply integrate this expression within lower limit to upper limit, that is x equal to r to a. You will get the potential due to rest part, and if you add these two terms, you will get the total potential due to the entire solid sphere. This is obviously for solid sphere, and P is located inside. P is located inside. Okay, so this is easy. So this is our first task. Sorry. Now in today's lecture, I will discuss an important issue, which is also you have heard the name of Laplace's equation. Okay, so we have to find out the Laplace's equation. Okay, so let's do it. Okay, now suppose Laplace's equation, while deriving, we have to consider a system of attracting particles, that there must be a potential exist. Okay, so to derive Laplace's equation, so you need potential. So we have to consider a system where potential exists. That means simply we take a system of attracting particles. Okay, here we consider a system of attracting particles. This must remember, system of attracting particles. So suppose V be the potential. Okay, now suppose P is a point whose coordinate is x, y, z, and we consider a particle, such a particle, say its coordinate is a, b, c. Okay, m is the mass of a single particle of the system whose coordinate is a, b, c, and if the distance is r, then from coordinate geometry we know the formula of the distance between 2 points on a line, which is simply what? Square root x minus a whole square, y minus b whole square, plus z minus c whole square. Okay, so P is considered a point P x y z and particular particle of mass m whose coordinate is a, b, c. So if their distances are, then from coordinate geometry we can write it. So what will be my r square? My r square will be x minus a whole square plus y minus b whole square plus z minus c whole square. Okay, now do some differentiation. So what will be 2r del x, we can write it 2 into x minus a. Okay, so from which we can write del r del x, this must be x minus a by r. So similarly we can write del r del y, this must be y minus b by r, and del r del z, this must be z minus c upon r. Okay, this is simply the calculation. Okay, now previously I told that V be the potential of the system of attracting particles. Okay, V be the potential of the system of attracting particles. So there must be an expression of V. Okay, V is related to the mass of the particle and the distance, that we all know. Okay, that we all know. What will be V? My V will be minus sum over of Gm by R, because here we consider a system of attracting particles. There are many particles, so we consider the summation. Okay, now from here we can write del V del R, this is equals to summation of Gm by R square. Okay, now what will be my del V del X? My del V del X will be del V del R del X. Now what will be del V del R? Sum over of Gm by R square. And what will be del R del X? Previously x minus a by R, that we give it R cube. Okay, so we have to find out del 2V del x2. So that means del x of this term. Okay, del x of this term means if you keep this fixed and do this, del x of this means 1. Okay, and if you take fix this and you have to do this, so del x of summation of Gm by R cube. Okay, so 1 by R cube, that means R means square. If you do it, then the result will be minus 3 by 2 R to the power 5. Okay, the result will be minus 3 by 2 R to the power 5, because you have to put R equals to root over x minus a whole square plus y minus b whole square plus z minus c whole square. Okay, and since you are doing differentiation with respect to x, there must be a 2x term. Okay, there must be a 2 into x minus a term. Okay, sorry, 2 into x minus a term, because R means x minus a whole square, y minus b whole square. So there will be a 2 into x minus a. Okay, so if we do del x of Gm by R cube, you have to put R equals to square root of x minus a whole square plus y minus b whole square, etc. And that you take, if you take it in, so that will be to the power minus half. That means minus half to the power 3 by 2. So that will be minus 3 by 2 R to the power 5 into this 2 cancel. So what will be the result? The result will be gm by r cube minus 3 into x minus a whole square by r to the power 5. Okay, this is the value of del 2v del x2. Now similarly, if we can write del 2v del y2 and del 2v del z2, we can write this. Okay, so what will be my del 2v del y2? This is simply summation gm by r cube, okay, minus 3 into y minus b whole square by r to the power 5, and we can write del 2v del z2, this equals to sum of gm by r cube minus 3 into z minus c whole square by r to the power 5. This is simple differentiation or nothing. Okay, now if you add these three equations, then what we get? You get the Laplacian operator del square v. Okay, so what will be the result? What will be the result? Okay, if you add these three terms, you will get del square v. This is equal to 3. This term will be 3 times, so 3 into sum of gm by r cube, and 3, if you take 3 common, there will be a term x minus a whole square plus y minus b whole square plus z minus c whole square by r to the power 5. Okay, so you can write 3 into sum of gm by r cube minus 3 into, this is means sorry, there will be a gm term will be common. Okay, gm term will be common, so 3gm, and this means r square divided by r to the power 5. Okay, so 3 into sum of gm by r cube, gm will be common in both terms. So gm by, this is also r cube, so this is 0. So simply this is differentiation. Okay, so this equation is called the Laplace's equation for potential. Okay, this equation is what? This equation is Laplace's equation for potential. For graduation student, the proof is necessary, but higher secondary students can also do it, and if you don't do that, no problem. Okay, but for BSc first semester students, you must have to know how the equation comes and what is its significance. Okay, so this is the equation, Laplace's equation for potential. Del square v, this is equal to 0, Laplace's equation in 3D. Okay, so today I shall discuss about the gravitational potential due to a solid sphere and Laplace's equation, and in our next day I shall discuss about few other things, and will end this chapter. Okay, so dear guys, if you don't subscribe my channel, then kindly subscribe it and share it to your friends to get latest videos on physics. Okay, thank you.